Hello, students. This is lecture number three in the series of lectures on the topic of indexing. Today, we are ready to talk about database indexes. Okay, so where are we so far in the series? Um, we've talked about two data structures, the B tree and also the hash structure. But um, So far, these two data structures, they remain as data structures, if you understand what I mean. And they are not yet indexes to be used in database systems. Okay. So today, this lecture is about how to deploy these data structures to serve the purpose of indexing. Okay. Um, so our discussion will primarily focus on B trees because they are simply, more important than hashing in general, more important than any other data structures um, in database systems. Okay. And furthermore, we will primarily focus on the row store approach. If you still remember, other than row store, we also have column store. Basically, the principles are very similar, so I will briefly talk about column store at the end of the lecture. All right, now let's start with some basic definitions. So this is to remind you about the concept of file. You have heard about this several times already in my lectures. So basically, this is just a file which is no more special than a regular file in your operating system. So in row store, each relation is stored as a file. Okay. So physically speaking, a file is a sequence of blocks, okay? Sequence of blocks, which means, there is an ordering that you like to follow when you read the file, okay? Otherwise, um, the tuples will be read in an order that is different from um, the intended order in the original relation. Okay, so there is a logical sequence. So let's say in this example, the logical sequence says this is block A, so that's the first block, and this is block B, block C. Okay. Now pay attention. This is just a logical order. There's absolutely no requirement saying that this block A will have to be stored in some block with the smallest address. No, actually, the addresses of these blocks can be arbitrary. Um, and you are able to maintain the logical sequence by storing pointers. Okay, specifically, I don't really care where this B is. It could be before A, it could be after A, but as long as I store the address of B, say somewhere in A, and then always be able to jump to B after A, right? So similarly, you also want to store the address of C in this block B, okay? Yeah, I'm sure you get the idea. Um, in any case, a file is simply, a linked list. Okay, but it's a linked list on the disk. Okay, cool. Very nice. So here we have the definition for this so-called dense B-tree index. Well, this is not very complicated. I mean, the definition is not very complicated. Nevertheless, I think it would be useful to look at an example first, and then we're going to go back to the definition. So here we have a relation with schema ABC, three attributes, okay? And when you create an index, you have to specify what attribute on which you like to create this index. So let's just say that the attribute is B, okay? So it's the second attribute here. And pay attention, we're talking about dense and B-tree index, okay? Dense B-tree, okay? Well, let me explain to you what I have in this figure. This relation R, it has a lot of blocks. Okay, it's a file has a lot of blocks. And here I'm just showing you three blocks. And actually in each block, I show you a tuple, okay? So for example, this tuple, its B value is 68, okay? Its A value is actually here. I'm not showing it because it's not important. and also this value C, okay? Hey, what is this TADA? Well, I can tell you this is an ID. Actually, let's go back to the previous slide. Every tuple of this relation carries an ID, okay, an ID. And this ID is assigned by the system automatically, all right? It's not something that you have to worry about. But for every tuple, the system will assign an ID, okay? So here, this illustrates the idea. So this TADA, let's just say that this is the ID assigned to this tuple by the system, okay? Likewise, if you look at, oh, by the way, this block has address 76, okay? So now let's look at another block whose address is 80. Here it shows you a tuple whose B value is 53, and this is its tuple ID. Okay, so you get the idea. Good. Now let's talk about this dense B tree index. All right. So first of all, it's a B tree. As you can see, this is the tree here. This is the leaf level. Here is the root. Okay. So let's say this is a B plus tree. All the leaf nodes are linked from left to right. Okay. So here, this is one leaf node, and this is another leaf node. Okay. Cool. Well, let me show you uh, the information within a leaf node. So here we have three leaf entries. Okay, the way to read this is to do it like the following. Okay, so this is one leaf entry. All right, so this is the second, and that's the third. All right, so we've got three leaf entries here. Now pay attention, right? So this leaf entry has this two numbers together as the data element. All right, so this is, as you can see, the B value. Why are we talking about B? Because you just told me you would like to create the index on B, right? So this is the B value, 53. And also pay attention, this is kind of important. We also stored the tuple ID inside, okay, inside this leaf entry, all right? So uh, speaking about this terminology, data elements. Do you remember, in the last, not last, in the lecture, in the B-tree lecture, we said in a leaf node, you have a data element, right? So let me tell you, a data element consists of a pair, all right? So 53 and T32, okay? So why a pair? Why not just the B values? All right, so why is it a pair? Well, here, the next example is going to explain why. Look, these two guys, okay, so this leaf entry and this one here, they correspond to two tuples, right? Hey, pay attention. These two tuples, they got the same B value. Is what I'm saying? They got the same B value. And therefore, if you want to distinguish them, you also have to uh, record their tuple IDs, right? Together with inside the leaf entry here. Otherwise, you don't know which entry is for which tuple, right? So now it makes things perfectly clear. You can see this is 68T7. So without a doubt, we're talking about this tuple here. And here we're talking about this tuple. You got the idea, right? So this is why the B tree is actually created on pairs. Okay. So why do we have 68, 68? Well, this is because B is not necessarily the primary key of this relation, right? So you should allow such things to happen, right? So two tuples having the same index value, right? So this is 68. And therefore, if you think about it, you are actually creating this B tree on a multi-set, okay? So as I explained previously, the B tree will have to be created on a total order. So it's a comparison-based data structure. You know that it works as long as you have a total order, okay? So if you have a multi-set, and how can you create a total order on a multi-set? Now, this is something I explained in the class. This was actually a question I left open at the end of the B tree lecture, sorry, the B tree lecture notes. Okay, so if you go back to the lecture notes, you see I had a question here. So this is why the question is relevant. All right, the way you create a B tree on a multi-set, you have to break ties, right? You 68, 68. You have to distinguish the entries, and the way to break ties is to break ties by ID. You see what I mean? So you can see if they have the same entry. I'm sorry, if they have the same B value, and then you're gonna put the entry for the tuple with the smaller ID, right? So basically, you favor the one with the smaller ID, right? So that's why T7 is before T88. Okay, good. Very nice. So now you understand why a data element consists of a pair. Um, but you see every entry still has one more number, right? So this number, hey, what is that number? Well, this number is the address of the block containing, this particular tuple here. All right, so that's why it's 80. And you can see this is 91 because this tuple is stored in this block with the address 91. And, it's 76 here, so this is the 76. Uh-huh. You get the idea, right? So here, this is another leaf node. As you can see, again, sorted according to the B values and then, by ID, all right? But you don't have ties there. And I'm not showing you the pointers here because I run out of space in this picture. But you should get the idea, right? So why is it called a dance? Look, for every tuple, I have an entry corresponding to it. Okay, so for every tuple, I have an entry for it, right? So if this is the case, and then it's like, then this is a dense index, right? So later we will see the opposite. That will be called a sparse index. So for a sparse index, you no longer have one data element for one tuple. Okay, and there you will see it's much sparser in the sense that the data elements are much fewer than tuples. Okay, so that's dense B-tree index. Okay, you got the idea, right? So another question you might ask here is why do we have to store this 80, right? I mean, uh, in a regular B tree, when the B tree is used as a data structure, you don't really see this additional pointer there, right? I mean, a data element is just a data element and that's it, right? Well, you see, that is one major difference between the B tree as a data structure and a B tree as an index. All right, so as an index, you do want to provide a pointer because the ultimate purpose is not to find the data element. The ultimate purpose is actually find the tuple. You see what I mean? So we want to find this tuple um, by way of this B value. All right. So finding the data element is not the point. So that's why you like to have this pointer. Okay, you got the idea. Hey, just give me a minute. I just want to make sure that this is being recorded. If this is not being recorded, then I'm doing this. Basically, I'm wasting my time. Okay, so yes, it's being recorded. So now, sorry about that. Now we can proceed. Right. Okay, so that's the example. All right, very nice. Now let's go back to the formal definition. So that should be the way to learn. Okay, so examples are examples, but they cannot replace the formal definition. So next time I say I have a dense B-tree index on this attribute of this relation. Now, what I mean is, okay, so this index is created on a total order, okay, on the total order. Now, this is important, right? So the B tree is created on a total order, and it needs no more explanation, and you know exactly what I'm talking about, right? Because a B tree, as long as it's a total order, then you can create a B tree, right? So what is this total order? This total order is induced by the x values of the tuples in R. So that's pretty clear, right? So you want to compare tuples by the x values first, and then with ties broken by IDs, right? So this basically implies that you'll be storing x value and also an ID in each data element. Okay. Well, if you want, you can store anything else. What I'm saying is at least you have to store this X and also this ID, right? Okay, but for this B tree to serve as an index, at least you also have to store the pointer. Okay, if you want, once again, you can store along with this data element anything useful about the the tuple. If you want, if you wish, you can modify the B tree like that, right? But at least you have to store three things: the X value, the ID, and also the pointer. And you know they serve different purposes, right? I think I already explained this. For X value, that's pretty straightforward. For ID, that's basically for type breaking, so that you know if two tuples they got the same X value, which one you're talking about, right? And then finally, you want to have a pointer because you want to get to the tuple, not just stopping at the data element. Okay. All right. So that's the meaning of this dense B tree index. Okay. All right. So I'm going to um, now here I'm going to talk about something very important. As you will see later on, when we use the index to do queries, and then this concept, this clustered concept is going to play a very important role. Okay. All right. So here is a definition. Here we say a relation R is clustered on attribute X if in this file, right, the tuples are sorted by X, and if you have ties, multi-set, right, if you have ties and then the ties are broken by ID, which means a tuple with a smaller ID is going to go first. All right. So basically, this is saying this relation R is sorted by X. Okay, but um, instead of saying sorted, you often hear the term clustered. All right. Okay, so let's look at this example. So here, this R has many blocks in this file. Here, I'm showing you just two of those blocks. Okay, so in the first block, I'm showing you some tuples here, and then here are some tuples. And indeed, you can see these tuples, they are sorted by X. Okay, because you can see 50, 53, 68. So that's in ascending order. But if two tuples, they got the same B value, and then you want to compare their IDs, right? You want to favor the one with the smaller ID. All right, so that's the meaning of cluster. So basically, the file is clustered. Right? So, and by the way, this is a logical order, right? So you have to still have to chain two adjacent blocks in the logical order by pointers, right? So this is the way to link things up. Okay, link things up. Okay, good. All right, so this slide is showing you an example of a dense B-tree index on a clustered relation. All right, so here this relation is clustered on B. Um, and again, it's a dense index because, every tuple has a leaf entry, okay? No exception. Oops, where is the leaf entry of this tuple? Well, it's here. It's there, okay? Even though it's not shown, but you can imagine it's there. Anyway, so that's why it's a dense uh, index, okay? Dense index. All right, so you can see that, well, the pointers, they appear to be more regular, right? So if you compare this example to this one here, what's the difference? Still remember the difference? Here, the file is not clustered, all right? Not clustered. So you can see that the pointers, they seem to be sort of like chaotic, right? But here they seem to follow some patterns, right? 7076, they come together. You see what I mean? So um, this is to reflect the fact that the file has already been sorted. Okay, nice. So where are we so far? So we understand what it means by dense B-tree index, and also we understand what it means by clustered. Okay. Now moving on, I'm going to talk about sparse index. Okay, sparse index. Here is the formal definition, but again, let's look at an example first. Right. Now here, again, same as before, I got this relation ABC, and this relation is clustered on B. All right, so here, again, these are two blocks of this relation, and this relation, remember, has many blocks. Um, nice, okay. By the way, this is the B tree, all right, and this time this is sparse. You already know what is dense. Okay, so and this is not dense. You understand what I'm saying? This is not dense. Why not dense? Because you see, not every tuple has a leaf entry corresponding to it. So, for example, for this guy, you don't really see 53 in the B tree, right? Because this is 50, this is 68. You know, there's nothing in between, so you don't really see 53 there, right? So, and likewise, you know, you got this T80A, 60A. So this is here, right? It has a leaf entry. However, this guy does not have a leaf entry. Have you managed to spot the pattern here? Um, I can't hear you, so I'm doing this video. I wish I could hear you. Well, there is an interesting pattern. You see, every block sort of like offers a representative. Okay, so look, this block offers its smallest tuple. Okay, smallest tuple, and this tuple indeed has a has an entry, has an entry here, leaf entry. Okay, in fact, if you look at this leaf entry, this is sort of like a representative from this block, okay? So you could say one leaf entry corresponds to a block, and every block has a leaf entry, okay? It's just that in this leaf entry, you store uh, the smallest tuple in the block, the first tuple in the block, okay? Same thing, right? And this is another example. You can see you have you have this block here, you have this block, and say you take the smallest tuple, which is here, and then you create a leaf entry on it. So if this is the case, we say you have a sparse B-tree index. You see what I mean? Because you basically the number of leaf entries is precisely the number of blocks in the B-tree. uh, I'm so sorry, the number of blocks in the file of this relation. Okay, good. Well, here is something important. Okay, so you can see, you know, we don't really have something for 53 at the leaf level, right? So what if I want to look for 53? Well, in a dense B tree, this was not an issue, right? Because if you want to look for 53, you know, 53 has a data element there, right? So just go for the data element 53, and then there is a pointer pointing you to the block containing 53, right? So that's the dense part, the dense index. But what about the sparse counterpart, right? The sparse counterpart. So here, do I have to worry? Like if I'm looking for 53, how can I use such a sparse index to identify the tuple, right? Well, interestingly, you are able to do it. This is once again due to the fact that the relation has been clustered on B. Okay, has been clustered on B. Look, so all you have to do is to look for uh, a predecessor of 53. Okay, so you do a predecessor search, and when you reach this, yes, when you reach this leaf, right? So you look at all the B values here, and you identify the predecessor of 53 among these B values, right? So what do you get? You get 50. So that's why you want to follow this pointer here. Okay, you want to follow this pointer, and so you get to 76. So you open up this block and you look inside, and that's how you find this 53. Okay, that's how you find this 53. All right, so simple reasoning tells you that 53 cannot be inside this block because, you know, this block, the smallest tuple already has the value of 68, which is greater than 53, right? And everything after this block can only have tuples with even larger B values, and therefore 53 cannot be there. You see what I mean? So so that's why you are still able to perform search using a sparse index. Okay. So what's the main advantage of a sparse index? The main advantage is that, you know, you get to you get to store fewer leaf entries in the index. Okay, so the number of leaf entries once again is equivalent to the number of blocks. Okay, so this is much smaller than the dense index, right? Because in the dense index, you have to store one leaf entry for every single tuple, right? But here, you know, it's one entry for one block. Okay. On the other hand, I could tell you sparse, even though I mean this sounds like a reasonable idea, um, sparse indexes are not supported by every single database system. Okay, so it's not going to create too many differences. So typically, you will be able to save sort of like one IO because compared to a dense B tree, a sparse B tree would typically be having one less level. Okay, the height will be like one less. So from the IO perspective, this is saying you would be able to save one IO, but then um, one IO is probably not significant enough for people to provide support for this index. Um, so yeah, that's one reason. There are some other reasons as well. Overall, I can tell you the effect is that this sparse index idea remains an interesting and reasonable idea. However, this is not universally supported. Okay. So that's the example. Now let's look at the formal definition and see how we can define a sparse B-tree index formally. Okay. Again, we're talking about relation. And here we've got an attribute here. This is the attribute you want to index. Now, importantly, sparse index makes sense only if this R has already been sorted on X. Okay, why? Because just think about what I did, right? I said this 53 doesn't have any leaf entry here, but yet you can still find it using a sparse index thanks to the ordering that's been created, you know, on the tuples, right? And without the ordering, none of these things would make sense, right? So this relation will have to get sorted on X. That's a precondition for you to create a sparse B-tree index. So what you do is you look at every block of R, and then you identify the smallest tuple in that block, and then you want to add it to a set because basically this is the set that you will be creating the tree on. Okay, you're not creating the tree on all the B values, right? You're not creating the tree on all the tuples, right? You're just creating the tree on a subset of the tuples, right? So it's like one representative from each block. All right, good. So this is basically the idea. So you can see the trees created on, the total order defined over this subset of tuples. And in addition, you also have to store a pointer, right? So this is the pointer here, right? Okay, so this is the representative, but this is the pointer, right? So basically, two things, right? So the tree is created on the total order over these tuples. And furthermore, um, for indexing purposes, you also have to store a pointer. Okay, so that's the sparse B-tree index. Just to remind you, um, the difference between dense and sparse is that a dense index contains one leaf entry for every single tuple, right? But that's not the case for sparse. In a sparse index, every leaf entry corresponds to a block. Okay, good. All right, cool. Now, so we've already talked about a lot of concepts. So here, I want to tell you, a few more concepts, right? So we talked about what it means by a cluster relation, right? If a relation is a cluster, and then it means it's sorted on a certain attribute. Now, if you look at a B tree, right, the leaf level, right, the data elements are always sorted, right? So that's always true, right? If it's a B tree, and then the data elements will always have to get sorted, right? So now, if the relation is sorted on one attribute, and the data elements are also sorted on the same attribute. And then we say that the B tree is a cluster index. Okay, so for example, this is a cluster index, right? Because you can see um, the data elements are sorted by B, and the tuples are sorted by B as well, right? So it's the same ordering, right? So that's why this is a cluster index. Okay, by the way, a sparse index can also be um, um, a cluster index. All right. So I'm not saying that you would need to be dense. What I'm saying is the orderings ought to be the same. Okay. So the ordering here is on B uh, at the leaf level of the speech tree, and the ordering here is also on B, and that's enough. Okay. And here, this is also a cluster index. Okay, so this is a dense clustered index, right? It's dense. You can see the ordering here is on B, right? And the file is also on B. And therefore, this is a clustered dense index, dense cluster index. All right, now this is not a cluster index. Okay, this is a non-cluster index. In other words, non-cluster. Why? Because if you look at the data elements, they are sorted on B, right? No problem. However, you can see the ordering here is random. So you cannot say that the file has been sorted on B, right? And therefore, the two orderings are different. And therefore, this is not a cluster index. When this is not a cluster index, we call it a non-cluster index. Okay, so just the opposite, right? Good. Hey, you may also hear the term secondary index. So that's just another way to say to refer to a non-cluster index. Okay. All right. So very nice. Now you'll understand indexes. Okay, so basically what we have done is to migrate from data structures, um, basically the B tree, right? Migrate from the concept of data structures to indexes. So now you basically, if you want to use a data structure for the purpose of indexing, you have to pay attention to a few things. You have to pay attention to the multi-step thing. Also, you have to be able to store pointers so that you can get to the tuples you want, all right? Um, an index in general, this is something you should have learned from the prerequisite course there. The usage of an index is to quickly identify certain tuples without having to scan the file from the beginning, right? So that's the purpose of index, okay? So we'll see how we can utilize such kind of indexes to reduce the query time, okay, compared to not using any index, okay. So this is a great moment to talk about something related to query optimization. In the second half of the course, Professor Surev is going to give you a very good introduction. Actually, not more than an introduction. Professor Sarab is going to discuss query optimization thoroughly. But here, some heads up on the some heads up at the concept level. Basically, the idea is if you look at a single query, the same query, there is typically more than one way to process the query. Okay, so you can process the query in multiple ways. Actually, we'll see some of those ways later. Okay, so every way or more formally strategy is called even more formally a plan. Okay, so sometimes you hear me say query plan, and then this is basically one algorithm for answering the query correctly. Okay. Well, today our database systems are super smart. Okay, so database system will be able to um, conceive multiple alternative plans for the same query before actually answering the query, before actually going out there to the disk to retrieve the tuples in the query result. Okay, before everything, the database will plan out a lot of things. Okay, this is the optimization phase. So basically, conceptually, what this query optimization is doing is to try different plans, try to come up with different plans, and for every plan, it will calculate an estimated cost. All right, so this is estimated because it could be wrong. It could be a little bit different from the actual cost of the plan because you have not executed the plan, right? So you can only do prediction, right? However, the database is going to have a reasonable and usually accurate estimate for the cost of each plan. And then out of all these potential plans, the database is going to choose the one with the smallest estimated cost. Okay, so this is uh, making a lot of sense, right? Because the database tries to avoid bad plans, okay, and it tries to select a good plan. All right, yeah. So as you will see, this is going to sometimes it's going to have very dramatic effects. If you don't do this, if you happen to choose a bad plan, and then the query cost could be like 10 times or even 1,000 times higher. Okay, so this is fairly possible. So in the next few slides, I'm going to explain to you using several examples how indexes, in particular how B-tree indexes, can influence query optimization. Okay, can influence the decisions that are made by the database. All right. Now, from now on, I will focus exclusively on dense indexes. Okay, so dense indexes are everywhere. Okay, sparse indexes, they can also be incorporated into the discussion following the same principles. However, sparse indexes are, I would say, less important because they are not supported by every single database system. And plus, um, as long as you understand the principles on dense indexes, adapting those principles to work on sparse indexes is quite straightforward. Nice. Okay, now let's start to see some examples. Now, this is the first example. Um, so here we've got a relation. All right, this ABC, three attributes. And this relation is pretty big. Okay, 1 million tuples. Now, let's talk about blocks. Okay, so the relation is stored in 10,000 blocks. So if you do the math, you see each block contains 100 tuples, right? So now this is something important. This tells you how the relation is sorted. Okay, so the relation is sorted on A. This is going to be useful later. Okay. All right. Now you also know. Oh, by the way, these bullets, right? These bullets are facts that are collected by the query optimizer. Okay, query optimizer. See what I mean? Because we're doing query optimization, right? So query optimizer is a special program in a database system, and this optimizer is responsible for trying out different plans. And for those plans, it will come up with some estimates for the cost. Okay, so this is what we're going to do. All right, but the query optimizer is going to consult a lot of things. So these are the things that will be looked at by the optimizer. All right. Um, so some students, I mean, at this point, some students would typically say, "Hey, so much information to consider. Is that really what's happening in a real system?" Very much so. I guess the answer is very much so. Actually, much more than this. So we're just taking a glimpse of this query optimizer. Okay. All right. So where was I? Yeah, I already talked about the first three bullets. Now let's look at the fourth bullet, which says actually somebody has already created an index. This index is on attribute A. Okay, so let's circle this. Okay, so you do have an index, and this index is on attribute A, and also this is a B tree, and you even know how many levels it has. Okay, good, very nice. So now let's do business. All right, let's be serious. Now we've got an SQL query here. Okay, so you can see this is essentially a range query, right? We like to find all the tuples whose A values are at least 100 and at most 200, right? Okay. Hey, what is an obvious plan you can use, right? So this is sort of like the most trivial plan, something that always works. This is called a full scan. Okay, full scan. So what you do is simply read everything in R, right? So you just have to read all the blocks, but you don't have to read any index, right? You're not using the index at all. So you simply read all the blocks, and then the query optimizer is going to put an estimate of 10,000 here. Okay, so you see, that's the estimate, right? That's the estimate, right? Um, so in this case, this estimate is, of course, super accurate. Okay, good. Now, let's look at the same example. This is not, I'm not changing the example. I'm just repeating some of the information for your convenience. Still the same thing. And, this relation is cluster on A. And also this index is created on A, and the B tree has 3 levels. Okay. It's still same query as before. Okay, same query as before. Now, in order to discuss the second plan, we will need uh, say, fact, not fact. What should I say about this? Like one more statistic, okay, one more value to be consulted by the query optimizer. Again, this is the real thing, okay? So the query optimizer is going to come up with an estimate of how many tuples um, satisfy the query. Okay. So what did I say? This is an estimate because you have not actually executed the query yet, right? So you can only estimate this number. Okay. And then the query optimizer is going to estimate the cost of this query based on this number. So this K is an estimate. And of course, this K may not be totally precise. And therefore, the optimizer may not be able to have a perfect answer for the query cost. However, um, this is something that the database would be able to estimate fairly well, for such kind of query. Um, so this is actually something really clever in the database system. So we will not go into it, but if you have a chance to learn about selectivity estimation, you might hear things like sampling, histogram. So those are the standard techniques with which the database or the query optimizer is able to estimate a thing like this. Okay. So today, our purpose is to demonstrate the principles behind query optimization. So let's just say that somebody has given us this K for free. Okay, so let's just say that this K is a pretty good estimate. All right, so and then we're going to do the optimization based on this estimate. Okay, cool. So now here, this plan says you want to use the index. Okay, you want to use this index created on A. The thing is how, right? So here is how you can use the index to answer the queries. Look, this is the file. Okay, the file is on disk, right? But this is sorted by A. You see what I mean? Sorted by A. Okay, so if you look at those tuples, if you wonder those tuples, where those tuples can reside on the disk, in the file, okay, in the file, the logical file, and then you see that those tuples they will have to be um, consecutive. You see what I mean? Because they're sorted by A, right? So all those tuples, between 100 and 200, they will have to come together, right? Due to the sorted order, right? Sorted order, right? Good. So if this is the case, what can you do? So what can you do in order to answer this query? So what you can do is you first find the successor of 100, by descending a path, right? This is a unique path from the root to the leaf level. And then from this data element, you will jump, right? You will jump to, the beginning. Sorry, you would jump to the, I said beginning, right? So I should have said you would jump to the block uh, containing the tuple of this successor of 100. All right, so this is the here. Okay, so let's just say that this will be the first tuple that could satisfy your query, right? So let's say its key could be like 101, something like that, right? So this will be the first tuple um, whose A value is greater than 100, right? Of course, if 100 is in um, in the set, and then this will be 100 itself. Anyway, so this is the successor of yi, right? All right, and then you have already got to the beginning of this rep portion, right? And then what you have to do is simply to read through, right? To read through the entire rep portion, right? But you can do it on the file. Okay, you can do it on the file. Okay. So how do we calculate the cost though? Well, if you want to descend the B tree, right, to perform a predecessor search, and then you have to access three levels, right? Because that's the height of the tree, as stated here, right? So in this case, you should be ready to pay three IOs, right? So this is the reason why it's a free IO here. Okay. And then you get to this tuple T, and so this is the tuple T here. And then you will scan from here all the way to the end until you get out of this range, right? So the thing is, how many tuples are you going to read? You know, as an estimate, right? Sorry about that. So as an estimate, you are going to read in total k tuples, all right, k tuples. So the next question is if we're going to read k tuples on the file, and every block can contain 100 tuples, right? So how many blocks do you expect to read, right? So this is the question asked by the optimizer, right? So I guess the answer should be fairly clear. The optimizer would say, hey, k, and it's 100 tuples per block, right? So if I have to see k tuples, and then I'm going to read so many IOs, right? Of course, you should be taking the ceiling, okay? So here, 3 plus k over 100 taking the ceiling, this serves as a good estimate of the query cost, okay? All right. So now we've got two plans. As you can see, for each plan, the optimizer has predicted a cost for plan one, this is 10,000, and for plan two, this is the expression, right? So now the database is going to compare them, based on the value k, and then go for the plan with a smaller estimated cost. Okay. All right. So there was actually, I mean, for practice, there's actually another issue that is quite important, okay? But this is not something we can talk a lot about. This plan one, right? If you just look at the 10,000, this seems to be a very large number, okay? However, in one of the tutorials, if you still remember, I talked about the difference between sequential IOs and random IOs. What I mean, so if the file of this relation is stored nicely on the disk, which means the consecutive blocks are really stored sequentially on the disk, and then if you want to read um, one block and then go to the next block, you don't really have to pick the seek time and wait time every single time. You see what I mean? So I hope you still remember this exercise we discussed together. Anyway, to cut a long story short, if the file is stored nicely, and then you expect to spend much, much less time to read a block. Okay. On the other hand, if the file is stored sort of like in random blocks, and then for every block you have to pay 10 milliseconds because that's called a random IO. Okay. So remember, this is just a number of IOs. This is not really in terms of seconds. Okay, what the query optimizer has to do is to basically convert this into seconds, right? So of course, for that purpose, the query optimizer will have to take into account how sequential the file has been stored, right? So if it's entirely sequential, and maybe this is going to, be multiplied with 0.1 milliseconds. Otherwise, you'll have to do 10 milliseconds per IO. So this is going to be a huge difference. Okay. So anyway, just so you know, this is something that the optimizer will consider in practice. And for our classroom discussion, because I cannot tell you, how sequential this file is, right? So we'll stay with the I arrows. All right. So every time I ask you to do something like this, I will be very clear. I will say, hey, just count the number of I arrows. Okay. I'm not saying you have to give me the data or the estimates in terms of seconds. Okay. Okay, so that was the first example. Okay, so that was the first example. Now, let's look at another example and let's focus on the difference there. Okay, so this time, still we have this relation. Let me show it to you. So still ABC, same as before, right? Still, this relation has 10,000 blocks and every block has 100 tuples, same as before. Okay, so in total, you have 1 million tuples in the relation. Okay. All right, now pay attention this time. The relation is clustered on attribute B. All right, so things are sorted by B. Okay, they are not sorted by A. All right, when the tuples are sorted by B, there's no reason to believe that the tuples are also sorted by A. Let me repeat, right? The tuples are sorted by B, and there's no reason to assume that the tuples are at the same time also sorted by A, right? Because in general, there do not need to be any correlations between A and B, right? I mean, they can be arbitrary values. So this implies that the relation is not sorted by A, all right? So this is something very important, something we will have to take into account later, okay? All right, continuing still about the stats, about the facts. So here we've got an index and the index is created on this attribute A, okay? So if I ask you, is this index clustered or non-clustered? Well, I can't hear your answer, but the answer should be non-clustered. Okay, non-clustered. Remember, right? Data elements inside a B tree always sorted. All right. So in this B tree, the data elements are sorted by A, but the file itself is sorted by B. So you see they're different. Okay. Continuing with the stats, the B tree has 3 levels here. Each time you get now here, this is an additional piece of information you get. Okay, so every leaf node contains 200 data elements. All right, and we will need this later. Okay, before we didn't need it. So still the same query, still the same query. Okay, so it's the same query as we saw before. Let's consider the first plan. So the plan is not using the index, and then this is a stupid trivial plan. You know, there's nothing you can do but read everything. So this is 10,000 IOs, okay, because the relation is stored in 10,000 blocks. All right, good. Now let's look at another plan. And this plan, this time we try to use the index, okay? But this is a secondary index, okay? So let's see if this is going to make any difference. I can tell this is going to make significant differences. All right, let me circle the most important uh, numbers for you. So this is 10,000 blocks, you know, and every block 100 tuples, okay? So R is clustered on attribute B, okay? And now we've got an index on attribute A and 3 levels for the index, and every leaf node has 200 entries, okay? Again, you know, we assume that the optimizer has got a very good estimate on how many tuples would satisfy the query. Okay, good. So how would you be able to utilize the index to create find the tuples? All right, so this is the index. Okay, and here is the disk. Okay. Now, in the previous example, you know, in example 5, right? Still remember I was able to say the tuples that satisfy this range query. So this is a range query, right? Will come together in the file. However, here I can no longer say so. You see what I mean? Because this file is sorted by B. Okay, sorted by B. So if I want to ask you, if you want to find all those tuples that satisfy this range condition on A, and then those tuples can be anywhere. You see what I mean? It's sort of like, you know, I'm giving you the idea, right? So uh, the red tuples are the tuples satisfying the query, right? But they can be spread across the entire file. All right. So this is something that's very, very different. So now you can see if you want to go to the blocks containing those tuples, it could be huge, right? In the worst case, every single tuple, uh, each of these k tuples, right, could be in a different block, right? So that's going to be a very, very bad situation, okay? So how would you be able to utilize the index to your best advantage, let's just say, to your best advantage, okay? So I don't know about you, but this is what I would do. What I would do is I would first find all the data elements, okay, the leaf entries, satisfying the range condition. Okay, so this is saying, I want to find all those data elements. Now I emphasize, so these are the data elements, okay, 100 to 200, okay. At the leaf level, the data elements are always sorted. Um, by the way, this is 100, okay. Sorry for the handwriting. Anyway, so at the leaf level, the data elements are sorted, right? So I do have a range here, right? So this is the leaf level of the B tree, right? So this is what I can say, they are in consecutive blocks, okay? Consecutive blocks from 100 to 200, okay? And then from there, I'm going to follow the pointers. Okay, you see what I mean? So each tuple here, there is a pointer, and for every tuple, sorry, for every data element, there is a pointer pointing to the corresponding tuple, right? So this is how you go from the data elements, the leaf entries, to the tuples on the file. Okay, so this is the process, right? So if you think about it, how many I/O do you expect to do? So this time the calculation is different from before, right? Look, so here the entire B tree has 3 levels, right? And here, there are 2 internal levels. Okay, so this is the leaf level, right? But there are 2 internal levels. So when you do a range query, you perform a successor search, right? And then you scan uh, the leaf nodes at the leaf level, right? So there are 2 internal nodes you have to access. So that explains the 2 here. Now, what about this k over 200? Look, you have k data elements here. Why? Because this is a dense index, right? So for every tuple satisfying the query, you have a data element corresponding to it, right? So still remember the definition of a dense index, right? Okay, so in other words, this K tells us that there are exactly K leaf entries we have to retrieve. Okay, so this is why this 200 here is useful. Okay, because we know that each leaf node can store 200 entries, and in total, we need to read K leaf entries, right? So how many leaf nodes do I have to access? The answer is k over 200. Now remember, every leaf node occupies this block, right? So this gets turned into the number of IOs I perform. Okay. All right, but this is only the blue part, right? So 2 plus k over 200. This is only the blue part, but that's not the nightmare. You see what I mean? The nightmare, the performance bottleneck is actually determined by um, the IOs that you have to perform to locate all these red tuples. Okay, and now unfortunately, there's no trick you can perform here. In the worst case, um, you really have to accept the fact that these tuples are in different blocks, right? No matter how smart you are, you actually have to perform KIOs to retrieve K tuples, right? So you can see this is the huge difference between um, different sorted orders. Okay, so before this relation was sorted on A, so it was very good for, the sorted order is very good for a range query on A. Okay, however, now this sorted order is on B, and therefore this is pretty bad for this query. Okay. So overall, this is the estimated cost. Okay, so it's k here rather than k over 100. Okay, so in example 5, here it was k over 100, but here it's k. Okay, so that is the crucial difference. Okay, nice. So now you can see we've got two plans, we've got two estimates. This is 10,000, and here, when you work with a secondary index, the cost is actually a lot higher. Okay. So unless K is super small, I can tell you, the query optimizer oftentimes will opt for just a brute force scan. Okay, just full scan. Okay. This is something you will see in the project as well. Okay. So a very important takeaway message here is that a non-cluster index is not as good as a cluster index. Okay, a non-cluster index may require you to perform a lot of random IOs. Okay, so I think you should have already got the point. Okay, so this is example 6. Now, let's look at another example. So this example is almost the same as before. Let me point out the most important things for you. Still the same relation. Still you have 2,000 blocks and 100 tuples each, right? Again, the sorted order is on B, and this is very bad for our query, our range query on A. There is an index here, and this is again a secondary index. This is an index on A. Same, you got 3 levels, and every leaf node 200 leaf entries. Okay, still the same query. Okay, however, there's one crucial difference. Look, this is select A, select A. Okay, and if you look at the query before, it was select star. Okay, so this is the crucial difference. All right. So when you have select star, you need ABC, right? All the attributes, which is why you really have to go to the disk to fetch all these tuples. However, if you select A, and then all the information that you need is already in the index, so that you don't really need to look at the file. You see what I mean? Like this is the file, right? But you don't have to look at the file, right? You can say no to the file now, all right? Because every tuple satisfying your query has a data element in the B tree. Okay, so still remember the blue portion, right? So you perform a successor, and then you access a consecutive segment of the entries, right? So this is the blue portion, and once again, for every uh, tuple in the file satisfying your query, its A value is already stored somewhere. You see what I mean? All right. So since you only need to report the A values, right? You don't really need to scan the tuples in the file. All you have to do is to access the leaf entries, and all the A values are there. Okay, which is why the cost now is much smaller. All right, so if this is the cost, uh, I mean, this is something you would try in the project. You will see for this query, its cost is significantly lower than before. Okay, simply because you only have to access the index. Okay, so 2 levels here, and then all the leaf nodes containing um, the entries you want to retrieve. In total, you retrieve k entries, and every leaf node is good for storing 200 entries. So that's why this is the number of leaf nodes you need to read. Okay, all right. So no access to the file is necessary. Okay, so this is example 7. All right, so this example A is an important example. So this is also the most complicated example in this um, set of lecture notes in this PDF file. Okay, so let's uh, look at the stats. All right, so here we've got 10,000 blocks, 100 tuples per blocks. So that makes the total size 1 million. Okay. So here, this relation is cluster on attribute C. Okay. Um, Now pay attention, right? So this is not A and not B, but on C. Okay, so this is sorted by C, and therefore this is not sorted by A and it's not sorted by B either. Okay. Well, you have two indexes this time. One is this TA. So TA is a secondary index on A or non-cluster index on A. Okay, and similarly, this TB is a secondary index on B. Okay, so now you know that this both B trees have three levels, and in each leaf node you can fit 200 leaf entries. Okay, in each B tree. Okay, good. Now let's look at this query here. This query this time is a two-dimensional query. Okay, two-dimension. Why did I say it's two-dimension? Look, there were two conditions here, one on A and one on B, right? So you can consider A as one dimension and B as another dimension. And we have a range condition on each dimension, right? It's saying, between 100 and 200, and this is saying between 300 and 400. Okay, so we're looking for all those tuples that satisfy both conditions. Okay, again, the query optimizer is going to resort to some estimates. In particular, here it's going to derive three estimates. First is if I just talk about the first condition. Okay, how many tuples would satisfy just the condition on A, and how many would satisfy just the condition on B, and how many would satisfy both, right? So basically, this KAB is the number of tuples to be reported for the query. Okay, nice. All right, so let me show you. Well, by the way, you can always do the trivial plan. Okay, so I'm not going to explain the trivial plan anymore. The trivial plan is, just go for all the blocks, right? You can. That's something you can always do. So here, in this on this slide, the focus is to explain to you how you can. I mean, at least one strategy. This may not be the best strategy because you have to calculate the estimated cost anyway. So this is one strategy for using. Uh, this is one strategy that uses both indexes to perform the query. Okay, but you have to remember every index um, tackles just one attribute, one dimension, right? So you have two separate indexes. Okay, and how can you put together two separate indexes to find the tuples that qualify that satisfy conditions on two dimensions simultaneously, right? So that is the thing. Okay. So let me tell you what's going on here. And interestingly, this is the place where these TIDs will make will play an important role. Okay. Let me explain to you. Sorry, let's use the same color as before. Okay, so this is the index on TA. Okay, and this is the index on TB. Okay, and here is the disk. Okay, so you get the idea, right? So here is the disk. Okay, so again, if you look at the qualifying tuples, they can be anywhere, right? Because why? Because the tuples in the file are sorted by C. All right, sorted by C. So you cannot really expect that they will come together, right? Because these are the tuples qualifying uh, the condition, right? The search condition. So they satisfy the A, they satisfy the B, right? Okay. Anyway, so now let's look at the following strategy, right? So what if I first perform a range query in the first B tree. And this range query collects only the leaf entries that satisfy the A condition. So I repeat, right? So the A conditions from 100 to 200. Remember that, this 100 to 200 here, right? So I want to find the leaf entries only. Okay, the leaf entries falling into 100 and 200. This is possible because this index is created on A, right? So here, all these leaf entries are sorted by A. Okay. So in the same way, I would find all the leaf entries from this index, which is created on B, right? So I'm going to find all the leaf entries satisfying the B conditions. The B condition is also a range condition from 300 to 400. Okay. Well, now the thing is, you know, if you just look at one blue, say, segment, let's say here, right? You have no idea whether a particular tuple here simultaneously satisfies the B condition as well. All you know is, this tuple will have to satisfy the A condition. Okay, and likewise, you have no idea whether a tuple here satisfies the A condition, right? It definitely satisfies the B condition. But the thing is, still remember, right? For every leaf entry here, we store, besides the A value, what else do we store? Still remember, we store a tuple ID. Okay, we store a tuple ID. Okay, so this is the reason why the ID, I mean, this unique identifier plays a very important role. Okay, so you see, if an ID appears here, but not here, and then what do we know? We know that the tuple with this ID satisfy the A condition, but not the B condition. You see what I mean? Okay. On the other hand, if a tuple ID appears in both blue segments, now what can you say? Then you would say that this tuple satisfies both conditions. Okay. So this is exactly the idea, right? So let's assume that here the tuple IDs here in the blue part, right? So let's just say this is SA, right? So the SA is the set of tuple IDs in the blue part in the index on A, and likewise, let's define SB symmetrical, right? So here, essentially, what you want to do is to find the intersection. Okay, so you want to find you want to find those tuple IDs that appear in both SA and SB. Okay, so if we assume SA and SB fit in the main memory, this is typically the case. Okay, so we assume that this and this they both fit in the main memory, and then we can perform the intersection in the main memory. Okay, we can perform the intersection in the main memory. And then in this case, you will be able to identify those tuple IDs. Let's say I'm just showing you the tuple IDs from the SA part, right? So you'll be able to identify those tuple IDs that appear in both places. Okay, you know what? I would show it with black color. So let's say in this case, we got 3 tuple IDs in both SA and SB. All right, so they might look something like this. Okay, but they will appear in both SA and SB, right? And now you are able to follow the pointer to find the corresponding red tuples. Okay, of course you should have the same number of red tuples as the black tuple IDs that you found there. Okay, so this is to give you the idea of the strategy. Okay, to summarize, the key idea of this strategy is to leverage the tuple IDs that you store in an index. Okay, so you leverage the tuple ID and you do the intersection. Okay, um, um, on the tuple IDs, and so that the tuple IDs that survive this intersection correspond to those tuples that satisfy both conditions at the same time, right? And then you can go ahead and pay 1 IO for each tuple ID to retrieve the corresponding tuple. You see what I mean? All right, so this is a useful strategy. And this is particularly useful if you do not really have too many tuples to report eventually. Okay. Now let's look at the IO. I hope the IO analysis should have become, I hope the analysis has already become quite easy and obvious to you. So if you look at the left part, what is the IO cost? So first of all, you have to descend 2 levels, and then you read a segment of leaf nodes, right? I mean, a set of leaf nodes. And how many do you read? Of course, it depends on how many leaf entries you have. Now, we have seen this before, right? So it's Ka and over how many leaf entries you can squeeze into one leaf. So basically, this is the number of leaf nodes that you have to read. The same thing applies to the other index. But after you have performed the intersection, the topology intersection, you still have to pay one IO, typically a random IO, to retrieve each qualifying tuple. Okay, so overall, this is the cost estimate. Okay, so hopefully this gives you a good idea about well, not a good idea. I mean some preliminary ideas of what's going on in query optimization. However, I think these examples have illustrated quite well, right? How you can utilize indexes in different ways to answer queries in different scenarios. Overall, query processing is a very creative process. And I can tell you, um, database systems today have implemented really, really sophisticated strategies, okay, different execution plans. All the plans that I explained using these examples um, can definitely be found and be deployed by a database system. Okay, so the database system will consider all these plans, and for each plan, they will come up with an estimate. In practice, this estimate might also needs to consider um, seconds as well. How many random or sequential IOs you actually perform as I explained, right? So overall, you can see the database system is trying very hard to plan out the execution and trying to select a plan that is as fast as possible, all right? However, everything is about the disk performance, okay? Almost in no circumstances would the database system consider CPU time. Okay, very, very rarely. Okay, and for a simple query like this, it's almost always about the disk performance. Okay, very nice. I still have a few things to talk about, basically some easy things. Now I will move on to talk about hash indexes. Before I start, I want to tell you hash indexes are not as important as B-tree indexes. Okay, so hash indexes, they are not supported by every database system. They are supported by, for example, PostgreSQL. So this is the database system we'll be doing our project with. Okay. Well, in some situations, the hash indexes might be able to give you a little bit of improvement over the B tree. But to be honest, the improvement is very limited unless in situations where the B tree is super tall. By super tall, I mean it has a lot of levels. However, to be honest, that also happens very, very rarely. In practice, typically the height of the B tree is like 3 or 4, so that's not very tall. Anyway, so let's look at how hash structure can be utilized for indexing. Okay, so this is the formal definition, but let's first understand the basic ideas from an example. Okay, so here this is a relation. Once again, this is a relation with schema ABC, and this time we have a hash index on attribute B of this relation. So still remember when you create a hash index, when you create a hash index, you actually have two parts. Okay, so the first part is this hash table, and then if you remember the length of the hash table, it has one cell, one address for each bucket. Okay, so the total number of cells here is precisely the number of buckets. Okay, and then here I show you two buckets. All right, so this is one bucket, that's another bucket, and so this is the address of the bucket, and this address is kept in the hash table. Okay, good. And here, again, I'm showing you two blocks in the file of this relation. And this relation has many blocks as usual, and these are just two of them. Okay. So you can see here, um, the ordering of the tuples does not really matter that much because the hash function is going to, sort of like scramble, the hash values anyway. So, no particular ordering of this relation is going to benefit significantly um, the query, which is the dictionary search, right? So we'll see the query example later. But this is sort of like giving you the ideas. Say you create this hash structure over the set of b values. All right. So now for example, you have this 53, and along with this 53, you also want to store like the tuple ID as usual, right? You want to be able to distinguish different uh, uh, different elements corresponding to the same b value, right? You want to distinguish different tuples with the same value, b value, right? And of course, you also have to store a pointer, right? Because you know, this is the pointer that you rely on to find the corresponding tuple, right? Just in case you also need the other attribute values. So this gives you the general idea of what a hash index looks like. Okay. All right, so let's go back to talk about the formal definition. I think this should be fairly easy to you now. This is the relation, and you got an attribute here, so that's x. Um, so you want to create this hash structure. This is a hash structure, right? You want to create it over the x values of the tuples in R, right? So you may have duplicates here, so it's not necessarily a set. So for each x value, you also have to store, as I said, the ID of the corresponding tuple, and also a pointer to the block where I can find this tuple. Right? So that's basically what we already explained. So here, this slide tells you what happens when you want to use a hash index to answer a query. So the query that we're talking about here is a point query. Okay, so this is the point query. We're looking for a equal to 53. So what happens is you do dictionary search over the hash structure. This is something explained in the last lecture. You first identify the address of the bucket. So you come here, and then you go inside the bucket, and you locate this 53 entry. Okay, if there are multiple entries with 53, you have to identify all of them. So for every entry, you look at this 80. So this is the block containing the corresponding tuple. We want select star here, right? So that's why we also have to look for A and C. So that's how you jump to this block, right? So if you have only one tuple satisfying the query, and then, I'm so sorry. I don't know why this is A. This is such a horrible mistake, right? So this should be B, right? Because I said, this is created on B. Sorry about that. Okay, so I'll get this corrected in my slides. Anyway, so continuing the example, if there's only one tuple satisfying the query, and then what will be the IO cost? The IO cost is typically two. Okay, so one is for reading the bucket. Okay, you can assume that the bucket is small enough to fit into one block. Okay, so that would be a fair assumption in practice because you can use a reasonably large number of buckets. Okay. Anyway, so that's one IO, and then you need another IO to go to the block, right? So all in all, it's two IOs, right? But there is a requirement here. The requirement is to assume that the hash table fits in the main memory, has already been loaded into the main memory. That's not always true, but it could be true. Sometimes, the database will actually load the hash table into the main memory in advance, simply because the hash table is very small, as I explained last time. Nice. All right, so we're coming to the end of the lecture. So far, I've been talking about row store. So let me quickly give you the principles behind column store. Okay, so basically the principles are pretty much the same as what we already discussed about row store. Okay, so still remember what column store is? In general, if you have a relation with D attributes, you want to store each attribute into a file. And this is the reason why a relation, usually is associated with D files rather than just one file. Okay. Now let's say this is the file for the attribute AI. Okay, so you have D of them, F1, F2 to FD. Okay. So you can see in each file, there is a logical order, right? So you will be seeing a sequence of values there, right? So let's just say that, this is F1, and then F1 is a sequence of values, F2 is sequence of values, and so on and so forth, right? So now you have to remember uh, each value is just for one attribute. Whenever I need, I will have to put together values in different files so that I can form a complete tuple, right? So oftentimes we will have to do things like select star. So for a query like this, you really have to put together the values from D files in order to form a tuple, okay? So for this reason, um, the values they will have to follow a very specific order, okay? Because you have to do precision alignment. You see what I'm saying? For example, if the tuple that I'm looking for, it's a1 value, right? It's stored at the ith position, and then basically you will be forced. You must. I mean, you are obliged to store the a2 value of the same tuple at the same position, the ith position. And actually, this has to be true for every single attribute. All right. And therefore, if you look at the ordering of the values in the file, the orderings um, they aim to achieve the purpose of precision alignment, so that when you want to concatenate different values into the same tuple, you can do this in DIOs. So I mean, this is like a huge number. Yeah, indeed. But the cost will be even higher if you don't do precision alignment. But even if you do precision alignment, even you carry out address calculation, right? You can do this in DIOs, right? You still have to do DIOs, right? So two IOs so far and all the way to the last file. You still have to do DIOs. Okay. So what's the implication? What's the takeaway message of this? The implication is that for the files, right? So the orderings are sort of like already determined by something else. Okay, so you cannot typically you cannot assume that the file is sorted by the attribute. Okay, you cannot assume, for example, this is sorted by A1, this is sorted by A2. No, this is rarely true. Okay, in practice, no, the ordering of the file is not determined by the values. Okay, it's determined by considerations and factors related to position alignment. Okay, and therefore, if you want to index this file, you can think about this as a one attribute relation, right? Each file, you can think about it as just one attribute relation. You can still index this relation based on the principle of dense indexes. Okay, dense indexes. You have to use dense indexes, and this dense index, inside the dense index, right? The data elements are sorted by, for example, for this file, it would be sorted by A1, and therefore it's going to be a secondary dense indexes. Okay, I mean, these indexes would be secondary non-clustered indexes. Okay. And then if you want to answer queries, so I don't really have examples here. If you want to answer queries, the principles that we already talked about for row store also apply here. Okay. All right. I hope these things make sense to you. I hope you have learned something about indexes. And thank you very much for your attention. Okay, so I will see you in the next lecture.